All right, everybody, I guess you guys are out there somewhere. And I happen to be here. And I just managed to get the screen on my computer, which I think you're able to see. And the way I did that was, I think somebody had suggested last time that I actually use a capability of Zoom uh, to just get me my iPad on my computer screen. So that happened, it seems, and I'm going to be using this methodology, this technique to actually conduct my lectures. So just to be sure, I assume that everybody is able to see what is on the screen.
Yep.
Okay. Yep. Right. Any issues? Any technical issues is what I'm basically asking for. You're able to see it, correct?
Yes.
All right. Thank you. So last time we began to talk about, I just gave you an overview of the class, what it would be like, and what kind of things we're going to talk about in this class. I just shared with you the syllabus that is posted on the at the University of Maryland schedule of classes site, so everybody understands. That's what we're going to deliver. That's the purpose of this class, and that's how we're going to proceed. So in that context, I'm going to start basically telling you a little bit now more about, the introductory sort of like transitional ideas. So last time we, sort of like got exposed to this thing called store program concept, which I also call von Neumann architecture. Um, and in this architecture, I sort of like display to you this diagram. We drew this together last time. We got these buses that connect memory on the left to the CPU, the central processing unit on the right. And there's typically a monitor and a keyboard, as you can see that I also drew those. And so this collection of these things, together with a bunch of other things like printers, scanners, and other kinds of things that you may actually, like maybe wireless input, for example, or output situations. You could have a lot of other things built on this. There are all these things called north and south bridges inside these CPU layouts. If you actually open your own computer, you can see those. Um, and in some sense, there are all kinds of other basically ports, the SCSI ports, other kinds of ports, the USBs and so on. So you know that this is a lot more than what it is, but we're interested in figuring out the most basic things, because, like sometimes we seem to like know something, but we don't really know it because we kind of know it at a level that is pretty shallow. Like, if somebody did, sort of dug into your knowledge domain, you probably have another sentence or two to make, but that's where you stop, because you kind of like speak in terms of cliches, the words that people actually utter at you when you go to, maybe a computer store, or you read up on things on the web. But that's a very cursory and a shallow knowledge in a way. So we will kind of go deep, a little bit deeper in one of those areas, maybe several of those areas, but initially in one of those areas, and that's the central processing unit, right? We will understand exactly how that thing works, not just like it's a central processing unit and it just processes things, which is obvious. And that's not what we want to know. And you probably can imagine that this is like there's a memory, CPU, monitor, keyboard, all these other things. This is a very high level representation of something. And so as a result, um, we just now basically what I'm suggesting that we do, we go past this representation and then try to see what happens. And after all, we coin this sort of idea, not just by ourselves, but by everybody who works in this field, as the so-called von Neumann architecture, right? So we're going to learn about the von Neumann architecture. That's basically one of the things that we want to do in this class. And we can boil it down to the CPU that you see here. We can boil it down to basically this thing right down here, right there. That is the CPU, the central processing unit. Maybe I should write it here. Central processing unit. Let's see if I actually write it here somewhere. Central processing unit, aka CPU. Okay, just in case you want to, just know what that is. You probably know what it is, just that I want to write it down. So now we got this, CPU, and we want to provide an example for it, just so that we understand what the CPU, and the CPU is going to do something that is very repetitious, meaning it's going to do the same thing all the time. It's not.
Excuse me, Professor.
Yes, Mark.
I'm sorry to interrupt. I think there might be somebody in the waiting room. Someone in the group me is saying they can't
Yeah,
get in.
I appreciate that. There's a bunch of people. I don't know why they need to be admitted, because I thought that, if they log in their accounts, they should be able to get here. But I appreciate that, Mark. Yeah, please holler, or just let me know if you see anything that is, needing my attention. I appreciate it. Thank you. And so what was I saying? I was just saying that, yeah, so there's a fetch, decode, execute process, and that's all we do. That's what a computer do. Now, you learn some tools. Let me actually grab my tea, because I was just boiling my water to pour myself some tea. Just give me 1 second. So as I was saying, if you were to do something like this, the diagram that you see here, if I were to do this in, for example, in terms of ENEE350 components, like, the gates that you learn about, or the flip-flops, or the registers, etc., that'll take a lot of effort to basically assemble this. I'm just suggesting that, suppose that we use some kind of a machine like Mealy or a Moore architecture, finite state machine, and you try to create all of the things that this von Neumann architecture will perform. Okay, and that will be a ton of work. You will probably have, considering a simple computer that may have just nothing but just a scratch pad of maybe 2 registers, let's say, right? Let's not go beyond that. Today's machines have in excess of 256 or so registers. Some of them do, not all of them. But even if you just start with some maybe 2 meager registers with maybe 32 bits each. Again, today's machines are 64 bits, but never mind. So in total, you're going to have basically 2 times 32 bits of information that you have to have in those 2 registers, and every one of those bits can be 0 or 1. So imagining that this machine that we call the von Neumann architecture, has the capability to go into each and every one of those states, and we could say, why not? Because those are arbitrary values that we put in and out of these registers when we actually program computers like this. So you have 64 bits, each of which can be 1 or 0. So even if you don't consider anything else, like all the computations that you have to perform, some, maybe storage you may need for those, and then forget about the memory that I showed you over there. You're going to have a finite state machine with 2 raised to 64 states, right? You learn in ENEE350 that a bit is a flip-flop. The output of a flip-flop is either 0 or 1, and that's just a bit. 64 of them put together is going to give you 2 raised to 64 states. And now you want to write a finite state machine, a Mealy or a Moore machine, that's going to have 2 to the 64 states, and you're going to draw all those transitions between those 2 to the 64 states. Now your life will not suffice for that. Not my life added to your life will suffice for that. Not everybody on this planet's lives added together will not suffice for that. Not the life of the universe or several universes will not suffice for that. So you understand that you cannot design a computer if in fact you're stuck with Mealy and Moore architectures that you learned in ENEE350. Those things are good for, simple problems like a Coke machine or this machine or that machine where you have maybe about 10 states at the most. So we cannot use the techniques of ENEE350 to actually design a computer, which is just a part of this, by the way. This CPU, the central processor unit, is the kind of brain of this computer that we're going to create. All right, having said all of that, there is an architecture that I designed for this class. I made it as simple as possible because it's not in the complexity that we find its virtue, but rather in its simplicity. Meaning that, if I made it more complex, your understanding would only get more complex, but the net value that you get out of learning this will be actually somewhat the same as if you had maybe some very, very powerful 500 some maybe plus instruction machine architecture like an Intel chip or so. Okay, so I'm going to use that vest, but before I get to that, I have to I have to tell you what this machine is like. I'm going to basically show you the Xcode where we can actually play with this. That's one of the advantages. Certainly I can simulate Intel chips, no problem. I could do them in no time. But when I do that, I may end up paying, some money to the University of Maryland, may end up paying some money to Intel, some other companies. I don't want to do that either. That's why we create here. That's why we do things the way we do, okay? And if you get hired by Intel or some other company, they're going to sort of like train you in 6 months and they're going to pay some handsome salary for getting trained. Some of you may actually have interned at companies like Intel, and you know what I'm referring to. So there's no need for me to tell you about Intel chips or MIPS chips or that other chips, right? That's just a commercial product that you guys can go out and find out when you intern for these companies or some other way. All right, so now that I said that, let me just, define this machine a little bit for you. So when you define a machine, one of the first things that you have to do is to sort of like create what we call an instruction format. Because these things that I wrote down here, fetch, decode, execute, they all refer to instructions, okay? So let me just actually put something here saying that I'm going to be switching to lecture 2. Okay, not that. Maybe I could just go to another page, brand new page here, just make it lecture 2. Okay. So we're going to talk about then instructions, okay? Instructions. Instructions are important. Everything that we do inside a computer is about handling instructions at the level that we're looking at, okay? So they are fetched, decoded, and executed. Okay, that's what we do with these things. Fetch, decode, and execute. That's that loop that I showed you. So we can fetch them, as I showed you over here, from the memory. This is like our program, I said, if you just remember. I said, this is our program. And we have a program over there. We're going to fetch them one at a time. So let me just basically bring that up a little bit more into focus. So this is what I'm referring to. Let's say that we have this, either what we call this an instruction buffer, sometimes memory. In our case, we're going to call them, memory to begin with. But sometimes, commercial machines place them in instruction buffers, so they're going to be there. But, for our purposes, we're going to have this memory here. And just so that, I have something very simple. Actually, I want to move this all the way down to here. Let me just go back a little bit. So just to repeat what we did, I'm just going to place a couple of instructions, maybe 3. Okay, so there are 3 instructions in here. Instruction 1, okay, instruction 2, and then instruction 3. Only 3. This is a program. This is my computer program. I got 1, 2, 3, basically, just like fetch, decode, execute. Okay. So this is my program, our program. So what we do, we fetch the first instruction. Okay. Fetch instruction 1. Decode it. Execute it. Fetch instruction 2. Decode it. Execute it. Okay. Let's just write that last one so that I tell you that this can go on forever. Instruction 3, decode it and execute it. Okay. Now, if we want to execute these instructions, forever, computer basically will do this by itself. We don't have to do it, except to point to the computer that we want to go back to the first instruction. Okay. So that's what the computer will help us do once we tell them to go back and execute from the beginning. Or we could, in fact, not have a jump instruction that'll take us back to the beginning, and there could be another instruction right below that, and we'll continue in this manner. Okay. So this is really an infinite loop as far as the computer itself is concerned. It just keeps like waiting for something to be executed, fetch, decode, and executed. And it's going to do that forever. That ease, that simplicity is what von Neumann architecture provides us. We don't have to worry about, once we get that first location pointed out to the computer, the processor, we need not have to worry about, what the computer is going to do after this. It's just simply going to find it, and then the next instruction, and so on. Now, for us to be able to execute an instruction, we have to decode it. And to decode means understand something, right? You probably, if you looked at my webpage, you saw something that's at the very top of the screen, where I simply talk about, science versus engineering, where I simply say that science is an encoder, whereas engineering is decoder. One encodes and one decodes. And I wrote that in, I put that in there, in reverse, so that when you look at that, you think that it's some sort of antique Latin sort of expression. But if you hover on that thing, that'll just simply decode it for you, like an engineer would do, and you will see what it actually says. I just, you can try that on your own after class. Just at the very top in my University of Maryland site, there is something that seems to be some odd language that you've never seen before. Just put your computer, your cursor on it, and you'll see what it is. So now we have to do decode and execute. So in order to be able to decode something, we have to have a name for it, right? I mean, like, nobody would be able to know who I am unless they know my name, except my maybe closest relatives. So they know me by name, by my name. So I have to give each and every one of these instructions a name, right? So we have to have a name for an instruction, right? So let's just say that, okay? Instruction formats. Okay. Now, typically, we have at least two fields. We have a name, and we have something that says, this instruction does something like this. So here's the opcode. Here's the operation, or the operand, maybe. We know what the opcode says. It just says add, divide, something. So this is the name of the instruction.
Sarah.
Yeah.
Hi, what did you write there? Opcode, and then what's the in front?
Okay. After opcode, I wrote operand.
Operand. Okay, thanks.
Yeah, you're welcome. Name of the instruction is what we call the operand. And operand is the I guess entity or the sort of like thing that we. Okay. This is what the instruction processes. Okay, so we take that operand and we do something to it. For example, let's say it's a number. We increment it, okay? Or we complement it. Now, this is just what we call a one operand instruction format. There's only one operand in here. We could have two operands. We could have three operands. We could actually have a lot of operands. You can stretch this instruction format this way and put more and more operands into it. But this is the simplest maybe. In fact, the simplest would be one without even an operand in there. An opcode will be just an instruction. We shall see such instructions when we look at stack machines later on, okay? Stack machines are those machines that actually have basically, except for push and pop, as we call them, don't have any operand to go with because they actually handle all of their computations out of a place called a stack, and stack has all the operands we need. In other words, operands are implied. They are not explicit. All right, I just want to take a sip here. So let's just, maybe look at this in the context of our first machine. And so you would recognize, what this is like. Okay. So here's our VESP architecture. Okay. And we call it VESP 1.0 architecture. Has 8 instructions. Okay. And now we're going to have the opcodes written. Okay. But let me just fill this space here. They are used to add, complement, move, or load, move, jump. There's a U in there, but we abbreviate it as jump. Jump if 0, and then a jump if positive, and halt. Okay, halt the CPU. And that's our VESP 1.0 architecture. So let's now make a table which shows how the opcodes are created for this, what opcodes are. So we're going to use a 16-bit instruction word. Originally or initially, I'm going to put some 3 bits into the opcode area. I'm going to make that go up to 4 bits later. For right now, it's going to be 3 bits. So these 3 bits will be my opcode area. So this is my opcode. And remaining 13 bits will be used, will provide an address. Okay, to an operand. or an address to jump to. We want to jump to a location. Okay, so 13 bits in there. No. 13 bits of information there. Okay, so you get the general idea that this machine is going to have 16 bits, 16-bit instruction. Instruction words. Okay, now let's just go ahead and actually define what these instructions are. I wrote them already, but I'm going to basically now make a table. So the opcode on the left, let me just create this sort of nice table. If I could actually use one of these. Okay, here's my table. And I'm going to put the opcode here. I can actually draw a line here. Okay. See if this lets me draw a line here. It actually does. Okay. So this is my opcode area here. Okay. So let's write these opcodes 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. We're all writing them in bits. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now the instructions, this we call the add instruction. Let's see if I can actually write them just like this. I'll divide this into another maybe place. I'll abbreviate them to some mnemonic. Okay. The first one is add. The next one is complement. The one after that is load. The one after that is move. Move with a V. And then jump. And then jump F0. And then jump if positive. And then halt. Okay. So that's how my machine is created. And when I put these opcodes in my instructions, my computer will understand that's what I want to do. If it sees a 000 in the opcode field, says, well, the user wants to add something, and so on, right? In complement, load, move, jump if 0, jump if plus, jump, halt, and so on. So that's how the opcodes help us understand what the instruction wants to do. But now we have to give context to these so-called operations, because opcodes will tell us what instructions we want to do, but they don't really necessarily spell out how the computer underneath is supposed to do these things. So VESP 1.0 is what I call an accumulator machine, okay? A machine that happens to have a very special register, which is known as its accumulator. Okay, so VESP 1.0, let's just actually use the space, is an accumulator machine. Okay, there's an N in there. I apologize for my handwriting because it's very difficult, and I seem to have also a little bit of an issue with my pinky here. And so when I write, sometimes it doesn't actually come out as well as, but the nice part about this technology is actually I have this capability, which can get me correct things in a very nice and neat way. It's fairly clear that's machine. So what that means is that we have this thing called a register, okay? But it also has on top of it a co-accumulator, which is what we call register B, okay? It has an accumulator, A, and a co-accumulator, okay, B. So we got these two registers that actually will occupy the topmost locations in our memory. Let me just show that to you, just briefly. When we look at our memory map in VESP, let me just do it this way. This is our accumulator right there. And this is our co-accumulator. So this is location 0, okay? I'm gonna write it on this side. I'm gonna write this in hexadecimal, 0x, okay? And I'm gonna assume for the time being, this is only 12 bits. You know, assume that I stretch the opcode by 1 bit, and just to keep things simple, so I can write them in 12 bits. Otherwise, I could actually maybe write this in, you know, let's just write this in complete 14 bits, because we're gonna write things in hexadecimal. If I cannot fit them into 12 bits, then my next stop will be 16 bits. As you know, that in hexadecimal, we go in like, you know, quantities of 4 bits. So if I could just say this is location, absolute location 0, 0, 0. And the next one is 0, 0, 0, 1. We're going to knock out the first bit of these 4-bit representations when we actually switch to 12 bits as we sort of like increase this size of this. And otherwise, we could actually use 13 bits, so the leftmost bit could be 0 in this case, okay? So this is our A, and this is our B. So when I say add, I am simply instructing my computer to do the following. I say A is equal to A plus B. Just do this for me is all I'm saying to it. That's what that opcode simply instructs the computer to do. It'll simply add A and B together and put the result into A. That's what it does. That's what its job is. Now the next instruction is complement. So it's going to take A and it's going to complement it bit by bit. This is the C notation I'm using it here. And complement A and put it back into A. That's a complement, bitwise, right? So if A were to be something like, you know, let's say if this is actually 16 bits, let's just do these examples maybe after I finish writing the rest of the instructions. I can illustrate to you what, in fact, these operations are all about. And the load instruction is a kind of instruction that uses 2 of these 16-bit words, okay? So when you look at a load instruction, load instruction will be part of my program. By the way, this rest of the space for the time being, okay, this space, this space is available to store our programs and operands or data. But the first two locations are off limits. That means we cannot put any programs in there, because if we did, we're going to end up creating a mess, because those are the two places with which our instructions will operate. And as a result, if our programs go in there, then we're going to ultimately adding and complementing and doing other things to our instructions themselves, and that will be somewhat deadly for a computer to get into. Now, this sort of like sectioning is done all the time inside computers. Operating systems at a much higher level, kernels also, excuse me, to some extent, you know, put the brakes on anybody who wants to penetrate into some location or space where, you know, some directories are located, some very secure locations, we call them, system files, you know, other kinds of places that are located in there. Never get fooled by the fact that you can actually see the system files on your own, you know, MacBook or Windows machine. The reason that you can do that is because it's your machine. Someone coming from outside would not be able to do that. But you can do it because you are the so-called the root of your computer if you choose to be, unless you're sharing with your computer with somebody and then that person is, you know, not letting you to get into those system files. But if you're the root, the system, the super user, then you can actually go and see whatever is in each and every one of those system files. Okay, but typically you're not going to be allowed to do that on an ordinary machine. Now, when you do that, you become a hacker. You know, sometimes you become famous and sometimes you become infamous. I mean, it depends on how people look at you when you become a hacker. Okay, your friends may actually sort of like pat you in the back and say, "Well, what a smart guy you are." But the FBI may come after you and then book you, and you know, and then you may actually spend some time in prison for it. So, but anyway, so the short end of the stick is that we don't really get to have people go to all kinds of places. In our kind of particular case, we don't let people to write anything into A and B in the form of instructions. Instructions are not supposed to be there. They are dedicated locations, and we only use them for our operations. Okay.
Professor, quick question.
Yes, Gabriel.
So this diagram you're drawing here, this is the memory, correct?
This one that at the bottom, yes.
Yeah, okay, cool, thank you.
No,
And so these are like A and B are registers?
Yes, they are registers, and we kind of like, you know, this is our address space, you know, like that when our bus goes to places on our computer, you know, bus basically can be loaded with lots of bits, zeros and ones, and those zeros and ones will point to locations in my computer. And so when I see 0, 0, 0, 4 zeros, let's say 3 zeros followed by a 1, they are pointing to these two particular locations in my memory, which I will use as dedicated registers for carrying operations like add and complement and load and move and so on.
Got it, thank you.
Yep, you're welcome. All right, now, so let's just continue. I was just going to tell you about the load instruction. So the load instruction kind of is, you know, a particular instruction. We can maybe, for example, have a load instruction in here, right there. No, not that way, this way. So this load instruction is going to occupy two consecutive locations, okay? Whereas the add instruction and the complement instruction will only occupy one. The load instruction is going to take up two of these 16-bit words. So that will be a load instruction. It's going to have its opcode, like here, which must be 00010, that is. So that's going to tell me that this is a load instruction, okay? Then I have two other things. One is the address to which I'm going to load something. So this is called the destination address. And this is the operand. So when I see or encounter this instruction, which happens to have that code 010, what I need to do is to take this operand that sits right underneath that first 16-bit word, part of my instruction, which is the load instruction in this case. It grabs that operand and places it into a location in the memory whose address is given by those 13 bits that I dubbed as my destination address for this instruction, okay? That's the load instruction. That's what it's going to do. Basically, it's going to take an operand, okay, and move it into, let me see if I can write it in a nice way. It's going to basically, let's say that well, let me just basically just say this. Yes, it's basically load. I'll describe this on the next slide. I don't have enough space to write everything here, but I could say this briefly. Copy operand. Maybe I should not say copy, but say load. Okay. And then I will say move. Let's look at a move instruction. So this was our load instruction. Let's just call this load. Okay. The next instruction I'm going to put down here, for demonstration is what we call a move instruction. So I'm going to draw the move instruction. It's also going to take some 32 bits of information to describe, okay? But now the opcode, if you notice, the move has the opcode of 011, as you can see it here, right? This is 011. So I'm going to write in here 011, okay? I'm sorry about that. Just change the color to this. 011 in this space. And then I have two more things to say or to specify. What would they be? Well, they will be, first of all, destination address as before.
Professor, did you purposely skip a row?
Did I purposely what?
Skip a row?
Hold on. Did I purposely do what again?
Skip one row. You didn't
Well,
write.
yeah, but I didn't, put something right next to it. I didn't purposely do it, but I don't want to, basically clutter my description. It's just an instruction. I can put them anywhere I want.
Okay.
Yeah, right. Mhm. Okay, so now the next place is not going to be an operand, but a source address. So this is the distinction between these two instructions. Okay, so this will be a source address. I can write this in full. So whereas the load instruction has a destination address that is glued to the opcode, as you can see it right here at the top, the move instruction has a destination address, just like how it was in the load instruction, but its second 16 bits carry an address in it, not an operand, as in the load case. This is what separates these two commands from one another. Now, so either I can load an operand, some value like 5, 10, minus 20, and so on, or I can point to an address, which is the source address, where some number, some value may be stored, like minus 5, 20, 10, etc. And that will be copied into this destination address, or the location that is pointed by the destination address. So this is something that will give us the ability to copy things from a bunch of locations in memory, the ladder instruction move. Whereas the first one is just there to load constants into certain locations in my computation.
So, Professor,
Yeah,
so basically the move is assigning a pointer to the source address
that's
and the
exactly right,
destination.
Jason. Yeah, that's like a pointer that points to a location where an operand will be. You're
Thank you.
absolutely, yeah. And that's how these two instructions differ from one another. Okay. I'll just simply, say and write it briefly, even though you can see what I'm intending to, just to keep this space compact here, move an operand. And we'll take a look at this in a more visual way on the next write-up that I'm going to share with you as I write these things. So the jump instruction is something very simple. What that does, it jumps it makes the program counter jump to a location in my program, which I can specify. Okay, so let's just say jump to a location. Okay, and this is jump to a location if 0. What is if 0? That is if the accumulator is equal to 0. Okay. Maybe I could say that here, since I seem to have used that second line here. If A is equal to 0. Okay. And the next one is jump if positive. Everything goes the same way. If A is greater than 0. And this is just, stop VESP. It just halts it, basically. It makes it stop execution. Its executions. Okay, now let's take take a closer look at these operations a little bit more, because I just sort of tease you into maybe wanting to learn this a little more completely. I think you got interested in, because now we got very specific. We were talking about generalities. All of a sudden now we have something in front of us, and indeed this machine exists for us. We have all the C code on ELMS. At any point in time, including now, you can touch that machine. It's going to run something. It's going to show you all the things that it's capable of doing. Again, it's because of all the things that we're doing here, like those 8 instructions I created. Once you create a machine like this, it empowers you, because you can actually go out and build it. And you don't have to use, some fancy language for it. You can take anything that you have. It could be any language that you're actually fluent in, and then you can do it anywhere, any way you like it. But let me just maybe, look a little more carefully to these 2 instructions, which I called load and move. Okay. Now, in order to understand these things, we have to introduce a few more things here. One of them would be what I call an instruction register. Another one will be a program counter. And another one will be memory address register. And the last one that we would need right now would be memory data register. So in order to implement, what do you understand from this word implement, by the way? What does it mean to you? Anybody can answer this question, because sometimes when I say implement, students ask me, what do you mean, professor, by implementing something? As if that you never heard of that word.
Perhaps using it?
Implement means using for you, Gopal?
Yes.
Okay, but that's a little incomplete in my mind. Any other ideas about what implement means?
To put something to work.
Okay, to put something to work. I think I like that better. To make it so that it actually works. It's not just an idea, but it's something that actually can be demonstrated. And it's implement. Like, implement your thoughts. Tell me how you're going to do it. Implement it for me. Okay. Now, another word that people use for this is realize. Realize it for me. Like, how would you realize this? How would you make it happen? Okay. That's what implement means. Show me a way that, you know, that you can really do this. You just wrote these instructions, but you didn't tell me exactly how you're going to do this. So I'm confused about it. I don't know how you're going to do this, right? It's easy to say that you want to load something from somewhere to somewhere. How are you going to do that? Show me the way to do it. That's what's called implementation. So in order to implement these two instructions, I need some additional registers, okay? So far we learned about two registers. We have two registers already. We already have, we need, let me just say this, okay? I got a little bit sidetracked here. The load and move instructions. We need two more registers. I guess I should not have broken it like this. And they are MAR and MDR. This we call memory address. Register. And we call this memory data register. Okay. Now, in order to implement the jump instructions, okay. We need another register, and that's called the program counter. Now, Intel calls it instruction counter, abbreviated as PC. They call it IC, or instruction counting, but we call it program counter. This is more, this is an older verbiage than what Intel uses in its architectural representations. So all in all, we have to have now, you know, as we were looking at this diagram earlier, where I showed you the CPU is kind of like beginning to take some shape. Let's draw that CPU one more time as we were, like, you know, developing this idea. So how does our CPU now look? Well, let's just put the CPU on this side. Let me actually do this. I like this capability, which gives me the ability to draw things in a very straight way, like so. So this CPU will have now at least two things in it, okay? IR, instruction register, program counter. Wait a minute. I didn't like this, and I have to go back to this. Okay. And even though we place them into, I guess what we call the memory locations, we have the images of these two things, which we call A and B. And A and B are registers here. Which then go into something called a ALU. This is called ALU. And this ALU actually kind of brings itself back into A. This is A, and this is B. And then right in the border or the boundary between this and the memory itself, let's just also draw the memory. Okay. We have these two things, which I, call them the interface. And this is our MAR, and this is our MDR. Okay. So they kind of exist between the memory itself. This is our memory. And these two things interact You notice that I drew the arrow in one direction when I put the MAR. It's actually going to project itself onto the memory to grab something. We're going to make use of some of the things you learned in ENEE350 to design a memory device or memory unit. But the MDR has bidirectional connection. As you can see, MDR both sends and receives. Because with MDR, we're going to either read or write things, whereas MAR is going to be providing the address. Okay. So let me just write that down. MAR holds an address. For an operand to be read from or written into MDR. Okay. Now, of course, when we write things, we use MDR to actually push the thing inside. That is inside the memory. When we read things, we get the MDR to receive things. So looking at it from the memory side, MDR is an outlet either to read something from it into MDR, basically read into MDR, and then from there we just simply read it into one of our A and B registers, if you like, registers. Or it could be used to write something into memory, and in which case, we simply push it from MDR into memory. Okay. So this is, let me just show this to you so that it's fairly clear. This arrow means write. And that arrow here means read. You can either read or write. When you write, you push the stuff in. When you read, you take it out. So the read and write words are with respect to the memory itself. We're writing into memory and we're reading from memory. Okay. Whereas this right up here is just the opposite, because I wanted to emphasize MDR here. Right. I mean, it makes sense to you. I hope that, when you have two things, you can either write from left to right or right to left. So there's potentially two conventions, but generally when we say write into memory, that means we grab something from MDR, put it into memory, and read something from memory means take it from the memory, put it into MDR. Okay. Let me just write this so that there's no room for confusion. Okay. general convention. Sorry about this. General convention is this. Read simply means from memory to MDR. Write means from MDR to memory. That's the general convention. Okay, so I get that. I think this is all in there. So now let's get back to the, we got about maybe 15 minutes to wrap the class. I'm looking at my time. Let's see if I can now make it a little more complete in terms of like, what we really do with respect to these two instructions that we just mentioned. All right, so here's the load instruction. So let's go back for a minute now. When I have this luxury, I just want to take advantage of it. Yeah, it's really nice. Okay, let us now return to load and move instructions. So let's look at the loop load first. Now, when I'm loading, let's just look at the map for it. Here's what I do. I take, here's my load instruction. I got this operand here. And I have my 0, 1, 0 for my load. Here is an address, which is the destination address. Okay. And so what happens is that the destination address points to a location here. It's an address. And then the operand goes over there. So, so we kind of move this operand here. Okay, that's what we do. So let's see how we mechanize this. In other words, how we automate this whole process. Okay. So now we have these registers. We should be able to do this. Okay, so what are our steps? What we have is an instruction that sits in the IR register. So let's just draw these things here. We got this IR register that actually currently holds our instruction. The IR instruction, that the instruction in IR is this particular instruction, which we call 0, load. Sorry. And then we have an address over here. And we have an operand down here, right next to it. Okay, this is IR. And we know that the operand is right next to it. Okay. Now, when we're executing instructions, our program counter keeps track of the things that we want to do. What that means is that as I'm executing this instruction, I place my program counter, the address in my program counter points to that location. And in anticipation of the next instruction that I'm going to execute, the PC gets incremented by 1, meaning that the PC is going to be looking at this location. So this is like, I will call it PC pointing here, and then PC plus is pointing to the operand, okay? So we get to increment the program counter by 1, and when we do that, all of a sudden program counter is actually looking at an operand as opposed to maybe an instruction. But that's just okay, because all we want to do at this point in time is to use the value of program counter to go and grab something from the memory, push it into the MDR, from where we then take it and then push it back into the address that happens to be sitting in the instruction register. So here are our steps. One, to load. Okay, copy PC into MAR. Okay. 2, read let me just use this, memory MAR into MDR. Okay, you do those things. So I copied PC into MAR, and I then read what MAR pointed to in the memory into MDR. So at this point in time, my operand is actually in MDR. All I have to do is to copy now the address portion of the instruction into MAR and perform a write instruction. Okay, so 3, copy instruction bits 3 through 15 into, copy that is, MAR, okay, and perform a write on memory. So let's write these one after the other. Let's see what these steps are, how we express them, you know, in the so-called RLT language, the register transfer language that we're creating here. So just let's follow this. Here's what we do. MAR is equal to PC. That's one step. And then we say MDR is equal to memory MAR. And then we say read is equal to 1, meaning that, you know, request a read. And then load MAR with instruction bits 3 through 15. Okay. And then finally, write back into memory MAR what is actually in MDR. And then issue a write equals 1. So this is the set of steps, the sequence of steps that we have to perform in order to be able to copy something that is, whose address is right next to our instruction word, which is our load instruction, and then push it or place it in a location whose address is given in the instruction word, right? If you just try to visualize this, let's see if we can actually visualize this, what exactly this is doing. Some, write-up that we have here. Let's see if I can actually contain it here. So here's what's happening. Let's look at this in the context of the memory, space we have. All right, so let's put our instruction here. Okay, let's identify all the steps. I think I made this a little too big. Okay. Now, as I said, the program counter was actually pointing to here. Let me just maybe put it over here. Here's the program counter. The program counter was pointing to this location. This is our load instruction, by the way. Okay. Program counter was pointing out to this place. And what I did, if you notice, let me just use the red. What this did right there, okay, look at that step. It grabbed PC, which is pointing out to this location, and placed it in here. It pushed it into here. That MAR equals PC just did that. Okay. And then after that, you notice what we did. Let's just use a different color here. We did the second one after this, which is this. So what that did was it actually used the MAR. MAR went into here, okay? And then we applied a read instruction or read command. And then you can see what happened. Something was grabbed out of memory and then placed into MDR. So what we did out of this, we took something out of here. Sorry about that. Let me just do this. I want to draw this, but in this color. This is our MDR. I got about 2 minutes to wrap this up. Okay. And then we grabbed it and pushed it into this thing, went into here. What is this called? A read. You see, we're reading. We just read what's in that place. That's our operand. So the blue one is implemented. The red one is implemented by way of this, right? This is the red thing that we just did. This is the red portion. The red kind of is identified with that operation. And then the blue one is going to basically involve these as I just drew it here.
I have a quick question.
All right.
Yes. Mm-hmm.
So is the PC pointing to the address or the operand itself?
The PC is always going to have an address that points to a location in memory.
Okay.
Yeah. Now the PC at this point in time is pointing to the location that is right below the instruction. That is the first part of the 2 16-bit word instruction.
Okay.
Right. The
So
load, the load instruction has 2 16-bit words glued together. Correct, John?
Yep.
And so the one below it is where now the PC points to, because we always increment PC by 1 every time we actually fetch an instruction, which
Okay.
I will explain in the next lecture most likely. Now, but you know, since the time is 1:45, I challenge you to basically complete this, you know, this painting process that I created here. The next thing that you have to do is to now bring IR into this. You know, I'm kind of like Fermat would say, I'm running out of my margin here. If I were to use another color, let's say, you know, just give it a try here. Let's just see, you know, green. So what I would do next time, I'm going to grab this green thing, as you can see it here. Just spare me some minute or two, and I have to explain this to, you know, like what happens. I haven't shown the IR in here. There's not much space left for IR, but if I had the space for IR, let's say that I actually squeeze it in here somewhere. Okay, let's call this IR. So this time you can see what happens. IR goes into MAR, right? That's what it is. So that is, now I'm going to take this IR, put it into MAR. And once I do that, I go back to my kind of, I think the opposite process, where now the direction of the computation will switch gears, and, you know, wherever that address is, which will actually point to somewhere here, maybe like here. And I'll be doing this. And how do I do it? By now pushing MDR, which is actually holding my operand already, into this place. So that will be like these two things together, basically. You know, if I can maybe wrap things up quickly here. So you can see the color coding kind of showing you what I'm doing. I did those 2 steps in one, the last 2, because I don't have a lot of time left. But so the diagram kind of is telling you what I've written in a linear way from step 1 to step 4, you know, in terms of the picture that we have in front of us, you know, how this copying, this loading really takes place in the case of a load instruction. Move instruction is a little bit more involved because we have indirection of sorts. We don't just grab the operand, we have to grab an address from where we have to get the operand. That means that we have an indirection in there. I will explain that, and then I will also explain this fetch, decode, execute process to you once I complete that discussion of, you know, how we get to do this move instruction. The jump instructions are easy. Okay, so let me just maybe briefly mention this. I'll just use another 2-3 minutes of your time. Okay, let me just say this. We will take care of the move instruction in next class. Jump instructions are real easy. Straightforward. And here's how we do them. In the force jump, we simply say PC is equal to IR 3 through 15. If it's jump if 0, that I represent this by 0, then if AC is equal to A, that is equal to 0, then PC is equal to IR 3 through 15. And the last one is jump if positive. If A is greater than 0, then PC is equal to IR 315. That's how you do jump instructions. And halt is actually even simpler. VESP, we call it VESP.reset is equal to 1. This is what makes the machine go back to its initial state. All right, everybody, I think we have come to an end of another class. And this time, I think we were able to use the full period of the lecture because we were able to actually get our internet working here on my end. Also, the technology kind of worked like a charm, as they say, and we didn't have any problems. Now I have some chat messages here, lots of questions.
Professor, I have a question.
Yeah, a little louder, please, Yekta.
Can you go back to the little thing we were drawing right now? Like go up a little.
Okay. See if I can do it here. Yeah, further up, like there.
Yes. So for the blue parts, I understand that you're saying we have like memory is going into MDR, but I don't understand why MAR is going into memory in that.
So MAR is like a pointer. It just like points to the place from where we have to grab something. It points to a place. It says grab it from there. Now you see that just prior to that, we conditioned MAR with PC because we said that PC will be pointing to our data, our operand, because we get to increment PC by 1 every time we actually fetch an instruction. And originally PC was pointing to this location. As soon as we fetched it, we also incremented by 1. This happens. I'm going to explain this to you when I actually go fetch, decode, execute parts of the process. So now we know that PC points to this location where our operand is. We put this into MAR first. That's what the red line did. And MAR is the utility, is the vehicle that actually points to the location where our operand is sitting. I need to get that out of there, put it into MDR so that I can put it into the place where the address, which is supposed to be here, is pointing to.
Okay, and could you please explain why you're pointing from the address to the memory, the green one, that it's going down?
So the green one is basically saying, now that I have, remember, when I copied this instruction 010 business, this portion was the address. What did I call this? Destination address, right? I called it the destination address, if you remember. If you go back here, you'll see that destination address right there. I'm going to grab that. Where is it sitting now? It's sitting right in the inside instruction register because that's where I have my instruction. And the portion, like those bits, 3 through 15, constitute the address that I need to shove this operand that I grabbed into MDR so that it goes in here. So I grabbed the destination from the instruction, put it into where? So just think about it this way, Ekta. Anytime I want to interact with the memory, I have to make use of those two things. One is MAR, the other one is MDR. MAR points to a location. MDR contains the data or the operand that I either push in or grab from memory.
Okay.
I cannot avoid those things. They are glued to the memory. That's how I relate to my memory. I have to go into a location. I have to specify MAR. Where am I going to go into memory? MAR tells me. What am I going to get from memory? It has to go to MDR. What am I pushing into MDR? Huh?
I understand the codes that we wrote. Like, I understand what they do, but like certain points that you drew were not mentioned in the codes. That's what I was recurring.
Well, I was trying to basically animate them by these diagrams that I've been drawing so that you can see what each piece is really doing with like MAR equals PC. So that means I have to copy PC into MAR. That's what I was trying to explain. Now that doesn't interact right away. So there's a portion of this process where I don't really deal with memory every time. That MAR equals PC simply means grab PC and put it into MAR. It doesn't go to memory yet. It hasn't yet. But the next step is going to read something because I put an address into MAR, and in that blue circle thing, I'm doing a read. Why am I reading? Because that's where my operand is. I want to put it into MDR. Now that I put it into MDR, I want to put it back into memory. Why? Because there's an address to which it must go. Where is the address? It's in the IR. I must copy it from the IR into MAR. Now that I got the address and I got the data in my MDR, I push it. So one is read, one is write, right? You see that? If I can just bring it back. So one is read, that there's a read, there's a write. There's a difference between. So first I read, now I'm writing. I took it out, I put it back. And the circles, colors are supposed to describe that if they do. Okay? Okay, everybody? We're all set, right? We're down to 21 students. And that means, they think so. Yeah. Any questions? Yeah, we can always hold some more time here. Yes.
I have a question. Does the address, or not, sorry, the operand, right? In like the first part of so the operand that constitutes bits 3 to 15, does that always point to the following bit? Like, is that an address? Like, is that just an address to the?
No. 315 is an arbitrary address. I load any address that I choose. That's why that green arrow thing that you see here is going to some arbitrary location there.
So then how do you load the second bit, the second 16-bit part of the load, right? Like the part that is directly below the...
I just grabbed it out of there in the first part of the first two instructions that you see there, MAR, MDR business.
Right.
They
So
grabbed them and put them into MDR.
Right. So in that line of code, you put okay. So that's because MAR at that point will have the second PC address, right? Okay.
Second location right after the instruction opcode 010 place, right after that. That's where it's pointing to.
Okay.
That's
where
I copied
MAR
PC into MAR, and then once I did that, I did a read, and what I read went into MDR.
I see. Okay. I see.
And then I push it back now to an any address that the user specifies in that destination place. That's the user's decision. Whatever he puts in there, that's where it goes.
So I guess what we're seeing is there's like an unseen PC plus in here, right? At
Yes,
what point
because
does that trigger?
Exact right. I didn't show you the fetch, decode, execute process. I'm just doing now the execution, basically.
Would that happen between red and blue?
Well, it will not happen between red and blue. I mean, there's a fetch process where I would increment. First, I have to grab this thing into the instruction register, which I haven't shown you here, right?
Okay.
I haven't shown you how the instruction came there. And so in that process of grabbing the instruction from the memory, I will increment the program counter after I actually grabbed it. And so that it'll be ready. It'll be pointing to that next location here, which you just see that 010 below that place. Okay. This happens all by itself. Okay. You don't, programmer doesn't have to worry about this. The programmer doesn't need to be concerned about it. The fetch process simply increments the program counter by 1, so that by the time you get to this place where you now have to execute it, you have the right value of program counter.
Okay, I see. I have a better sense of how this works now. Thank you.
Very good. All right, everybody. So I think we're all set, and we're down to 1 people or 2 or 3 people, including myself. That means that we probably should get done with the class. Yes, Shane. Yes, Shane.
Earlier you said operators or operands are not explicit, they are implied. I kind of missed what you meant by that.
Yeah, so when I do add, for example, right, I don't say exactly, what to add, what 2 numbers to add. I just simply assume that operands they're implied to be in A and B registers.
Oh, right.
They're
and
not,
yeah, I see what you mean. And another thing I kind of missed, I zoned out for a second. It sounded like you were saying something interesting. You said something like not everything in the universe will make out something about the register bits.
Oh yeah, so I said, what I said was that if you had just a simple computer with 2 registers like we have here, A and B, and ours are 16 bits, but let's say that you push them to 32 bits, so the two of them put together will be 64 bits, right? Right, you have 32-bit register, another 32-bit register will be totality will be like 64 bits, correct?
Yes.
Okay, so each of those bits can be 0 or 1, right?
Yep.
And you can put any numbers in there. Now you want to create a machine using maybe Mealy or Moore model or some sort of a state machine, diagram or a table. How many states would you have in this case? You got 64 flip-flops. How
It
many
would be
states?
like 2 to the
64.
64.
All right.
to the
Can you make a state table like this? Can you create a 2 to the 64 bit state table? Can you create it? Can you put it into some memory?
Yes.
You can. I mean, not conceptually. I'm talking physically. Can you specify all the transitions in that 2 to the 64? Draw some graph with 2 to the 64 vertices. Call them your states. All right.
Yes.
And now tell me all the transitions that your machine is going to do. You have to draw a lot of lines. Even if you
Right.
draw one line from one state to another, you're going to end up drawing 2 to the 64 lines, and your lifetime will not be enough to do that.
They were basically like saying that we couldn't simulate everything.
What
Or
I'm
that we
saying is
couldn't
that,
have,
what I'm basically saying is this, that you cannot design a computer, with that many states, just having 2 registers. I didn't even just put a third one, which will then push it to 2 to the 96 and so on. Even with 2 to the 64 states, you have to create, say that your computer is this machine that you just, drew as a Mealy diagram. And now, all your computations are about like changing these bits, right? You're adding, multiplying, comparing, whatever else you're doing. They all amount to like, we say we add A and B together, right? Whatever other computations you want to do, you have to specify what happens, what state you go to every time you add some number to another number, right? And then you can have any number in A and any number in B. So now your state transitions have to say, okay, this is where you go to this state now for this edition. For that edition, you go to this state. So many states that are difficult to draw in one's lifetime, in universe's lifetime, is all I said. If you just,
all right.
think about trying to draw this. I mean, like, and give yourself some time to draw it in. Maybe a computer will draw this, but where it's going to draw. By the way, today's machines, I think, cap around to 48-bit machines all we have. Like in virtual memory, kind of stops at 48 bits.
All right.
Multiply that
All right,
by
thanks.
2 to the 18. That much
18.
more memory you would need to actually, that's a lot of numbers, a lot of locations.
All right.
Does that make sense, Shane?
Yeah, I think I just kind of lost you on the last part about the memory, how many more locations.
Well, 2 to the 18 is a big number. It's about what is it? 2 to the 18 is 16 is 65,536. 18 has to be 256,000. And you're multiplying this large number, which we talked about, where the computers of today are capable to map by that kind of a number. And now you want to have that much memory. I mean, how much memory do you have on your computer, terabytes wise, right? What number is that?
Well, normally computers, they store like a terabyte of disk drive memory.
So let's say you have petabytes, right? Like 2 to the 15 bytes. I mean, 2 to the 18, what is that? Giga is 9, yeah, tera is 12, and peta is 15, isn't it?
Yeah, I think, or maybe it's pico. Or wait, no, that's I think that's something else.
Petabytes, yeah. They call them petabytes. Like, after tera comes peta. This is, zeta, order, and so all these things. But the peta is 2 to the 15, basically. Right. I mean, 2 to the 15, nobody has petabytes of memory on their personal computers. I think maybe, you take some of these machines together, you can go up to that because, it's just, it goes in like bits, 3 bits, 3 bits, 3 bits. Right? You go to from 6 to 9, 9 to 12, 12 to 15, etc. Right? So you have 2 to the 10 is like 1 kilobyte. 2 to the 16 is, I guess, 64 kilobytes, and then 2 to the 20 is like a megabyte, right? That's number of bits, basically. 2 to the 32, how many bytes is that? 4 gigabytes, isn't it? Are you following that?
I think.
2 to the 32 is like 4 gigabytes.
Yep.
And then you go push it to, I guess 35 becomes terabytes, and then 38 becomes petabytes, and so on. So 64 is like where you're headed in this case, in the simple example I mentioned. Bits, not bytes, but that's okay. That's the only 2 to the 3 part there, which is, so you stop at 2 to the 61 as opposed to 2 to the 64. So a lot of transitions, a lot of states that you won't be able to put onto any physical machine today.
Right.
That's all I was trying to say, nothing more. And of course, that's just a simple example. Typical machines today have lots of registers. I mean, like I think even MIPS has 32 registers, general purpose for GPRs, and then they have some floating point registers, etc. And you won't be able to represent all these transitions by drawing a Miller diagram for it, for the machine itself, the entire computer. It'll be impossible. Hope that makes sense, Shane.
Yeah, I see. Yeah, I just missed that part a little bit. It sounded interesting.
Yeah, you were late attending the class. Is that what you're saying? Or you didn't follow?
Well, I was just a few minutes late. I was just, I think I was in the middle. I think I just lost track a little bit there.
Yeah, just talking about it. Maybe you caught me when I maybe talked about it a little bit. All right, very good. So how's the class going so far?
I think it's going good. I'll have to study up and review stuff. Make sure I know my stuff.
Yeah. I mean, we're gonna be slow and deliberate. And any questions could they come up in your mind? Just simply shoot my way.
All right. Thanks. See you.
Take care now. Bye-bye. Just go through some of these chat messages here. Okay, some questions. All right. All right, we'll just stop sharing.